We'll start the recording. So the next one is the definition of the load patterns. The first one is the self-weight of the building. So for the self-weight of the structural member, select dead as a load pattern and keep the self-weight multiplier as 1. So please note that if you keep this factor as 0, the software will not calculate self-weight of the members and there will be a significant error in your model, right? So this is for the self-weight. And then for the live and dead loads, for the live load pattern and superimpose dead loads pattern, select live load pattern and super dead load patterns and keep self-weight multiplier as 0. Because if you take this factor as 1, the software will calculate weight of the members based on these load pattern as well. So there will be significant increase in your weight of the structure, and there will be many consequences of selecting this safe value multiplier from 0 to 1. So let us define these two, and then we'll go towards the earthquake definition of the load pattern. So we'll go to define, and when you click on this load pattern, so a window will appear in which already two load pattern has been defined by the ETABS. You can also define your own. For example, let us change its font. It is dead. So you have to select the dead from this type, and you have to add self multiplier for self weight of the structure as a 1. So click on modify because it was already here. You can also add it. So the live load, let us delete this and we will add live. So we will add live and we will select load pattern type as a live, and the self multiplier automatically software will take it 0, because if you take it 1, the software will also find the self weight of the members based on this live load as well. So we'll keep this as 0 and click on the add new load. So these are the two loads. So the next one is the SDL super dead load. We are superimposed dead load, and select the type as a super dead and keep this as 0 and click on add new load. So these two load pattern has 3 load pattern has been defined. The next one is the earthquake. If you are designing your structure for the earthquake, and you have to define those load patterns as well. If you are designing it for the gravity loads or for you are doing any research, so these 3 are enough. So the next one is the earthquake load pattern. For this, you have to select seismic load pattern and keep similarly keep the self-weight multiplier as 0 and select the desired code for which you want to define your earthquake, and then click on modify load pattern to insert the data of earthquake for the proposed building. For example, the data you will be needing is the zoning, what is the zone of your member, your proposed building, and what is the soil type on which the building will be constructed, and the approximate time period, etc. All of this data. And for these data will be obtained from the UBC 97, and you can also use the building code of Pakistan seismic provision 2007. Right, so these both codes are the same because building code of Pakistan is based on UBC 97. So let us go to the load pattern. We will name it as earthquake, and we have 2 directions with earthquake X, and on type we will select the seismic type. So when you click on seismic, this option is clickable now. So now you can select your desired code. These are the different number of codes you can select for your desired country or region you are working. So in our region, we are using UBC 97. We will click on this and we will add new load. So now this load has been added. So how to insert the data? You have to click on this earthquake X and click on the modify lateral load. So this window will appear, which will require the different data for your earthquake load definition, right? So the first one is the direction in eccentricity. Normally UBC 97 and other codes allows you to use this eccentricity, which is the 5% eccentricity. So when you unclick all of these, so this eccentricity will disappear. So there's no, because you are not taking any eccentricity in your building. So code allows you, permits you to use at least 5% of eccentricity in your structural numerical models. So we will defining this only in X direction. We will uncheck the Y direction. So in earthquake in X direction, earthquake in X plus eccentricity and earthquake in X plus minus eccentricity, and that eccentricity is 5%, 0.05. So these are the condition, direction, and eccentricity for the load pattern, seismic load pattern. The next one is the time period, and the other is story range. Further factors, this is our strength reduction factor R. This is response modification factor. The next one is the seismic coefficients. What is the soil type of your structure for on which you are designing, and what are the seismic zone factor, right? And then we have the, for example, if you are designing for zone 4, if you click on 2, these will disappear, and other factors are the seismic importance factor. So we will discuss these in our presentation one by one. So the first one is the approximate time period. It can be calculated using the equation given by the UBC 97 in section 5.30.22. It says that for all buildings, the value of T may be approximated from the following formula. And T is equal to CT into HN power 3 by 4. HN is the total, H is the total height of your building, and CT is a coefficient which is equal to 0.035 for steel moment resisting frame and 0.030 for reinforced concrete moment resisting frames and eccentrically braced frames. And for other buildings, it is 0.02. Other building means for brick masonry and confined brick masonry, you can take CT value as 0.02. So all the software is asking, you can see the time period, you can add your CT value in here, right? Or you can leave it on the software to calculate time periods. We have to insert this CT value that is for the reinforced concrete frame structure. The CT is 0.03. You can also go through this section in UBC 97 for Building Code of Pakistan. I have taken all of these notes from these codes. So for the reinforced concrete, it is 0.03. Right, so I have written this. So software will automatically calculate this T for you in order to calculate the base shear for your proposed building, right? So this is the equation where you can find the time period of your proposed building. So all you have to insert the CT value in your ETAB model, right? The next one is the overstrength factor, that is known as the response modification factor. This factor can be selected from the table 5.13, which is the Building Code of Pakistan, Seismic Provision 2007, right? So you have to select your structure system for which you are designing, and you have to select those desired R value and insert that in ETAB. So we are designing our, let me zoom it. So we are designing our moment resisting frame system, and it consists of different options. It is special moment SMRF, IMRF, OMRF, and other different combinations. So you have to select your desired, this is R value. So we're designing special moment resisting frame system. So there are different conditions and restrictions on what is SMRF, IMRF, OMRF. Let me conclude it very quickly, because you can see through different codes, and you can search on Google. And SMRF means you are giving very detailed information to the field engineers, so you can add in your structural drawings. For example, there is very small spacing in the ties and the stirrups in the columns and beams, and you are keeping everything according to the code which we code define what is SMRF. So we have to select the value of for the concrete 8.5. If you are not following any restricted values of the number of the ties and the spacing of ties, the hooks values, the development length, and if are not care for these, or you do not want any special requirements in your structures, you can select IMRF or OMRF. There is also codes permits you to use for the zone 2B and zone 1 and zone 2. you can use IMRF, and for zone 3 and 4 you will using the SMRF, but you can also use SMRF for zone 2 and zone 1, because there will be a significantly a small change in the reinforcement, because if you use SMRF, you are giving detailed information in the structural drawings. So the value of R will be 8.5. So on larger value, the share base share will be divided. So less demand will be on the structure. If you take the IMRF 5.5, so on smaller value, the base share will be divided. So more demand will be on the structure. So more reinforcement will be given by the software. So you can use SMRF in every zone, but in zone 3, and especially in zone 4, you can use IMRF. You have to go for the SMRF. So we are designing our structure as a SMRF. So we will select for the complete R value as a 8.5, right? So you will write is here 8.5. So there is a connection between the reinforcement in R. Let me explain it. For example, if you R value is 8.5, so let us compare this. Let me write 5.5. So let's assume this is R 5.5, this is R 8.5, right? So for the R 8.5, the base share will be less as compared to the R value of 8.5.5. So greater the R value, less will be the base share. Smaller the R value, more will be the base share. So less base share means less demand, more base share means more demand. So if there is more demand, so more reinforcement, it is less demand, so less reinforcement. So if you roughly speaking, so there will be no significant or more change in the reinforcement. It's almost equal to almost equal, right? So you can use any system, but you have to keep, if you are giving information or structural drawings according to SMRF, IMRF, so you have to select that value accordingly. So this was the whole story about the response modification factor. The next one is the soil type. It can be selected from UBC 97 in section 4.4. Structural engineer will get this information from about the soil type from geotechnical engineer, that is geotechnical report of the site on which this proposed building will build, right? So there are the different definition of the soil properties. For example, in a report, there will be shear wave velocity, which will the value of this will be given in geotechnical report, or simply the geotechnical report will say in conclusion and recommendation here that the soil type of the proposed site is SA, SB, SC, SD. SA is hard rock, SB is medium rock, SC is very dense soil, and SD is stiff soil, right? There are another two type of the soils, the SE and SF. So these are the definition of the SE and SF, and you will get the information about the type of the soil from the geotechnical report, whether it is SE or SF. So there is a sentence written in here that is in exception. When the soil properties are not known in sufficient detail to determine the soil profile, so generally SD shall be used. For example, if you're designing a structure, a very low, for example, 3 or 4 story building, and if the geotechnical investigation has not been carried out, so on conservative side, code permits you, allow you to use this type, soil of the type is an SD, stiff soil, right? So in our model, we'll be using, because we haven't done any geotechnical investigations, we will select SD because code is allowing you to use this SD if you do not have any geotechnical report data. So this is the soil type. The next one is seismic zone factor, which is Z, which depend upon the peak ground acceleration. So if your building is in zone 1, so the Z value is 0.075, it is 0.075 PGA, which is peak ground acceleration. For 2A, it is 0.15, 2B 0.2, and zone 3 and zone 4 is 0.3 and 0.4. So how will you know about the zone of your district or your city? So there is another table in Building Code of Pakistan. This is for the Punjab. So you have to go through these tables and select your desired city for which you are designing this proposed building, right? So these are different tables. This is for the Punjab, this is for the Balochistan, this is for the NWFP. So now we are designing our structure. Let's assume we are designing for the Peshawar. So Peshawar is lying in here. This is seismic zone. So for the Peshawar, it is 2B. And for the other, for example, if you are designing your structure for the Chetral, so you can see that it has been given the seismic zone as a 4. So you have to select those properties accordingly. Right? So we are designing for the Peshawar. Let us assume that the building is in Peshawar. So we will select the seismic zone as a 2B. Right? So this is for the Sindh, and you can select your design zone. So let us go to the ETAB. So we will select the seismic zone factor Z. This is for the zone 1, this is zone 1, and this is 2A, this is 2B, this is zone 3, and this is zone 4, right? So we click on zone 2B, and this CA and CV, these are the pseudo acceleration and pseudo velocity values. You can also insert these values and manually by selecting these values from the code. These values has been these are available in your code building code of Pakistan, and you will see and see. So we will select this option per code, and we have selected this. The next one is the seismic importance factor, and that is given by the UBC 97 in table. This is building code of Pakistan table 5.10 occupancy category, and these are the different categories given. For example, the first occupancy category is the essential facilities. This includes the having surgeries and emergency treatment like hospitals, right? And other, for example, for the designing a structure for the army, for the air force, you have to select this seismic importance factor I 1.25, right? So if you are designing a structure for wind, so there is a wind importance factor as well. So we are concerned with this seismic importance factor I. So that is 1.24 for the hospitals, for the army facilities, and all of these. So another is the hardious facilities, that is for the nuclear facilities, and all of these structure will be in importance factor is 1.25. Special occupancy structures, the buildings we are designing, residential buildings, schools, and all others are in this third category, and its importance factor is 1, right? So you can go to this and you can study it by yourself as well. So here for our structure, the importance factor is 1. So now we click on OK. Before going click on OK, there is a story range the software is asking on which range you want to apply these seismic forces. So we will select the basement, from the base to the top. The overhead water tank and the MOMTs are not included in the seismic distribution of the lateral forces. So we'll click on OK because we have selected our range from basement to top, and all of these are defined. So this is for the earthquake X. Now we will define for the earthquake Y. Same, new add new load, and then we modify lateral loads. So now we'll uncheck the X-axis. We'll select the soil type as SD to be on conservative side because we do not have any tech report. Zone 2. This is 0.2 means 0.2 PGA peak ground acceleration. This is 0.5, and this is 0.03 for the concrete, and we will select the top. This is R 8.5, importance factor 1. So all of these are okay. We click on OK. So click on OK. So the load pattern has been defined. This is what the host about how you use the UBC 97 to define earthquake forces for your proposed building. Now the next one is, this is interesting. Designing a building in zone 1, 2A, and 2B, and 3 is comparatively easy. But when you are designing your structure for zone 4, it requires an additional information that will be required in order to design that building. So in the next slide, we will discuss what are those information which we will need for designing your structure in zone 4. Right, so there are two factors that is defined in building code of Pakistan, that is table 5.18, near source factor NA, and the second one is the near source factor NV, right? So these two factors depend upon the seismic source type ABC and the closest distance to non-seismic source, that is the less than or equal to 2 kilometer and 5 kilometer. So if you are designing a structure, you must have the fault information, right? The faults are the elements in our earth structure which causes the earthquake, right? So these, you should know the seismic source type, and you should have enough information of the fault, right? What is the fault? So in the next slide, there is another table given in UBC 97 that what are the seismic source type, how will you define these? So this is the seismic source type. This is, for example, the seismic source type A is the fault that are capable of producing large magnitude events and having a high rate of seismic activity. So these are the values that will be given by the geotech report to the structural engineer if you are designing a structure in the seismic zone 4, right? So these two additional requirement factors you will need for designing a structure in seismic zone 4. In ETABS, if I go to the ETAB again and click on the load pattern, and if I'm designing my structure in seismic zone 4, if I select 0.4, automatically these two factors will be clickable. So now you can enter your an A and B in here, or you can, as per the code, you will select the seismic source type and the distance in kilometer, which is written in here in the kilometer for the NA and NB, all of these. So this was the whole story about how you will design your system in seismic zone 4, right? So now we have designed our define our load patterns. The next part is the load combination. You can add default load combinations in ETABS by clicking add default combo. It will generate the combination based on the code you have selected. We will define our load combination based on UBC 97 because there is no code in this ETAB because UBC 97 has been removed from ETAB. So these are the load combination given in UBC 97. These are the 1, 2, 3, 4, and then we have 6 combination, right? General combination. These are the general combination. You have to extract your information for which you are designing your building, right? So this is 1.4D, 1.4D plus 1.5, 1.6 life plus 0.5 LR. LR means roof load, and S means snow load, and W means wind load, right? And there are some coefficients F1 and F2 which are defined in here. That F1 is 1 for floors in places of public assembly when the live loads exceed from 100 PSF, and for all other floors it is 0.5. So our case is 0.5 because our live load is not exceeding from 100 PSF, right? So F2 is 0.7 for the roof configuration, all of these because we do not have any snow loads or roof load, because we will be giving the loads as per the floors for the roof as well, right? So the next thing is very interesting, that the code says that the factor load combination for this section multiplied by 1.5 for concrete and masonry, where load combination includes seismic forces. It means that if you are designing a structure, you are building only for gravity loads, so you do not have to multiply all of these, which includes the earthquake forces, by 1.1. But if you are designing a structure for seismic forces, you have to multiply those combinations which have the earthquake forces by 1.1, right? This means you have to multiply 1.5 factor to all those load combination containing earthquake loads. So how do we do this? Let us go to the next slide. So these are the load combinations, which is 1.4D for our proposed building. And we have 1.2D and 1.6 live because we do not have any roof load or snow load. So it becomes 0. So we were left with 1. This is 1.6 N, 1.6, right? So the third one is the 1.2D plus 0.5 live because we are having F1.5 for our case because our load is less than 100 psf, and this terms becomes 0. The next one is 1.2d, 1.3 wind. We do not have wind, so it becomes 0. F1, it is 0.5 L, so again it becomes this, so do not need to write that. The next one is the 1.2d plus 1e plus F1L plus F2S. So F2, so there is no snow load, so S will become 0. So we are left with the 1 times E and 0.5 L. So that is 1.D, 1 L and 0.5. Then the last one is the 0.9 D plus minus 1 times E or 1.3 wind. So you do not have wind, so it becomes 0.9 D. First is minus and then 0.9 D plus E, right? So for our case, we are designing it for the earthquake forces. So after multiplying 1.1 factor for X and Y direction, we have total 9 combinations, right? So these are the 9 combinations for our proposed structure, that is 1.4D, 1.2D. So these are the load combination which are being multiplied with 1.1 because it includes the earthquake forces. So we have multiplied these by and hence these load combination by 10%. So we will define these. So now you have to go to define load combinations, and now you can add the add default design combo by clicking here, but you can select your desired frame. It is concrete frame. You can click on OK. So the load combination based on the SCI 318.14 will be appeared because you have selected that code, right? So you can select that code from the design, concrete frame design, view, revise preferences. So now you can select your desired code from here. For example, you are using Mexican code, you click on OK. So when you define the default load combination, so it will be based on the Mexican code, right? So this is the Mexican code load combinations. So now you can cancel that and again go to designs complete because we are designing according to CI 318.14, right? Because we do not have any spectral acceleration and spectral acceleration for 1 second, spectral acceleration 0.2 seconds, that is defined in IBC and C716. We have the all data on building code of Pakistan, it is UBC 97. So that's why we are defining our all load combination for the proposed building. So first of all, we have to click on the a new combo and then name it whatever you want to name it. For example, if you want to name it 1.4D. So D means it consists of the dead load as well as the superimposed dead load. So you have to select the SDL and 1.4. So this is the first load combination we have defined. Now click on OK. Now take a copy of this combo, and now we have 1.2D plus 1.6 live. So now all you have to do is add new live, and this is 1.2. And this is 1.6. Now click on OK. Now add copy of this combo, and the next one is the 1.2D plus 0.5 live. This is 1.2 and we will make this 0.5 and you will write in here. Okay. The next one is the fourth one is 1.32D, 1.1 earthquake X plus 0.6 live. So this is 1.3 dead plus 1.1 earthquake X plus 1.0.6 live. So we will make this 1.32, 1.32. This is 0.6, and we will add earthquake X, and we will add 1.1. We'll take copy of this, and we will have this Y for the same combination. All you have to do is to change this y and change the earthquake xy in here. Click on OK. So now the next one is the 0.99d, which is minus 1.1 earthquake x. So 8 copy of this 0.99d minus 1.1 dx. So we will delete this live. And we will add minus sign in here. We will select earthquake x. Now we will take copy of this. And we will have plus earthquake x. We haven't changed this. Let us change that as well. 0.99. So now take copy of this and define 0.99d minus earthquake y. And take copy of this. You will have plus earthquake y. So these are the load combinations. This is 9 load combinations according to UBC 97. Because we are designing our structure, we have defined the load pattern of earthquake using UBC 97. Therefore, you have to use the load combination based on the UBC 97. Right. So these are the load combination that has been defined. The next one is the load cases. Load cases are automatically generated by the program for each load pattern. However, you can review or define your own load cases as well. So let us go to the load cases. Let me save this. Go to define load cases. So now we can see for all of those load patterns you have defined in your load patterns, the load cases has been defined automatically by the ETAB. So now you can go to modify load case. So now you can see the pattern is load pattern and the load name is dead, and keep the scale factor as 1, right? Because we have added this scale factor in the load combination, right? So this is the load cases. You can add your own new case. This is the load type. It is linear static, linear dynamic, whether it is construction stages, or it is response spectrum, it is time history, it is buckling. You can define your load case from here, right? So we are not interested in that because we are doing linear elastic design of a proposed building. The next and the last topic of this session is the mass source. The base shear is defined by UBC 97 in section 5.30.2 that the static force procedure, it is equivalent static force procedure, the base shear is equal to CVI divided by RT into W. So this CVI divided by RT is a coefficient which will be multiplied with the weight of the building. So this equation is actually telling you how much of the percentage of the weight will be applied as a base shear on the structure. For example, if the weight of the building is 100 units and this coefficient comes out to be 10, so it means that 10% of the weight of the structure will be applied as a base shear on the structure, and that base shear will be then distributed as a vertical forces on each story to determine the response of the structure, right? So in ETABS, you have to define mass source in order to find weight of the structure. To calculate this W, software will ask you about the mass source, from where I will ETABS is asking you in shape of the base mass source, that from where I have to define or I have to calculate the weight of the structure for you, and then use this weight in calculation of the base shear to apply those base shear at the base of your structure. I assume that you know what is base shear and what are the static load procedure, what is equivalent static force procedure, and how the structure or ETABS distribute those forces on each story, right? So these are different analytical procedures you should know, right? If you don't know, you can search it on Google, what is static force procedure and what is equivalent static force procedure, and how the base shear is distributed along the height of the building, right? So the next part is the effective seismic weight. The only dead loads are to be used in the calculation of the seismic weight. It is defined in AC 76 section 12.7.2, right? That the effective seismic weight W of the structure shall include dead load as defined in section 3.1 above the base and other loads based on the list below, right? So for the normal structures like residential buildings, commercial buildings, and all other hospitals and any structures, you have to select only the dead load. But in area where used for the storage like warehouses and storage areas, you have to take the 25% of the live load as well to be included in the definition of the mass source and seismic weight of the structure, right? For all other structures like residential buildings, other structure, only you have to take the dead load, that is self weight, and the superimposed dead load, right? So let us go and define this mass source. That is defined, go to the mass source, and there is a by default defined mass source. You have to modify this. Click on the modify show mass source. So name it mass source and uncheck the element self mass, additional mass. Click on the specify load pattern, and you have to add the dead, self weight of the structure, and SDL. Only these two, because code is permitting you to use these only dead load, that is the self weight and the superimposed dead load. If you click on this element self weight, right, so it means that you are calculating the dead self weight of the structure 2 times, because you have included the self weight here and you have this element self mass as well. If there is an additional mass you have added in the structure, you can click on this, otherwise uncheck these, right? So based on the code, so only click on the specified load pattern and select the only dead load, that is dead self weight, and SDL, that is the superimposed dead load, right? So for the storage purposes, you can also add the live as well, and you have to multiply that is with 0.25 to make it 25%, right? So you can add this live load for the storage purpose, but we do not need this in here because we do not have any storage in here. So this is the mass source, and this was the whole story about the concept of the mass source, or why the mass source is calculated and why do we need mass source. So the mass source is used to determine this effective seismic weight of the structure, or in the effective or seismic weight of the structure is used to determine the base shear of the structure, and this base shear will be applied on the structure in the form of the forces to check the effect of the structure in form of the earthquake forces, right? So this is the equivalent static force procedure. So this was the whole story about the load combination, load patterns, and the assignment of the sections, mass source, and how do we define all of these. So I think the session is over for the Zoom. I will end this and will come up again with the new link in WhatsApp. So you can quickly join this so we can have our question and answer session.